So we have done mole conversions and we looked at Avogadro's number, we looked at our molar mass, we have moved between units within the same element or the same compound. Now we're going to look at what happens when we need to move between compounds, between elements, between things that are in a reaction. So that chemical reaction we looked at in the last unit, we're going to now move forward and say, okay, if I start with this amount of compound A, how much product A will I make? Or if I use this much of compound A, how much of compound B do I need? Things like that. So that's what we're looking at. We're looking at the relationship of compounds and pieces of a reaction, and we're going to look at it mathematically. So stoichiometry is the quantitative, it's the numeric number relationship between the number of moles or masses of various products and reactants in a chemical reaction. Remember last unit I said that balanced equation is super important? This is why. It is right here. This stoichiometry is all based on the fact that you have a balanced equation. You have a balanced reaction. If you do not have a balanced equation, all of this is for naught. It'll be a terrible, terrible feeling and it won't work. And so we need to balance, balance, balance first. So if you need help with that, please work on that. But balancing the equation first is going to be our number one priority. So the reason we need that balance equation is we're going to make a ratio. So a ratio is a number to another number, and sometimes it's related to as a fraction. So it's like a 1 to 3 would be a 1 over 3. It's a fraction between the amount of moles between two compounds in a reaction. And so we need coefficients. Coefficients come when you balance equations. So we're going to put the moles we want. So we're going to look at our question and we're going to say, okay, what is the question asking us to find? Okay, what compound or what element is it asking us to find? We're going to use that coefficient, okay, for the top. And then we're going to have it as a fraction, and we're going to look at the moles given. So we're going to look at the problem. And we're going to say, okay, what is the compound or element that has a number attached to it? Okay, and we're going to say, oh, it's hydrogen, it's oxygen, it's whatever, it's calcium sulfate, whatever the question's asking for. The question says, whatever has a number, we're going to look at that one in our equation, our balanced chemical reaction equation, and we're going to put that one on the bottom. And so we're going to take a look at one really quickly. So here's my balanced equation. I have two H2s plus O2 yielding two H2Os. Okay, so that's what we're looking at. That's our balanced equation. Right now, I'm going to give you some balanced equations. Sometimes you might have to balance on your own, but I'm going to give you a balanced equation today. Okay, and my question's asking is saying, if I start with 5 grams of O2, how many moles of H2O am I going to make? Okay, so I'm going to start by figuring out my molar mass or my molar ratio. So I'm going to look at my thing, and what I'm looking for, if you notice, it says how many moles of H2O. Oh, and that's supposed to be H2O. I'm sorry, I missed the O. It's going to say, so I'm going to put that I have 2 moles of H2, and that's supposed to say O. Okay, over 1 mole of O2, and I'm just looking at my equation. There's a 2 in front here, and even though there's not a number here, I know that if I wrote O2, that I have a coefficient of 1. So that's my molar ratio. So for every 1 O2 molecule, I will make 2 H2O molecules. Okay? So when I'm going to convert between compounds, I'm going to take those mole conversions that we just did in lesson 1, and we're going to take them a step further. So we're going to make our mole conversion chart just a little bit longer. Just a little bit longer. Not too crazy, but just a little bit. Okay? So again, I'm using the question, if I have 5 grams of O2 makes how many moles of H2O? And again, I have my balanced equation. So 2H2 plus O2 equals 2H2O. So because I have the word grams in my problem, I need to find my molar mass. Anytime you see the following things, grams, the word mass, how much does it weigh, that is going to be an indication that you are going to need at some point molar mass. Okay, so I'm going to do the molar mass, and I'm going to do the molar mass of the word associated with grams. So in this case, grams of O2. That O of is a bridge to O2. Okay, and again, we've done this before in the past. What we're looking to do is we're going to look at our periodic table, okay, and we're going to find the average atomic mass, that's that number with the decimal point. And remember, we're going one decimal place after the decimal point. Okay, so oxygen is 16.0. And because it's O2, that means there's 2 oxygen atoms in this molecule. I have to account for every atom, okay, right? And so I have 32.0 grams per mole. That's going to be really important. That's going to be part of my factors as I'm converting. Okay, so I'm going to go ahead and draw my first piece, and I'm just going to do the quick conversion from grams to moles, right? Because that's what my problem's asking for. It's asking for the moles. Okay, so I'm going to convert, and the information I'm given is that I have 5 grams of O2, and I can see that in my problem right here. Okay, and then again, I'm going to do the same thing I did before. I'm going to use my conversion factor. I'm going to put the units given on the bottom, and I'm going to put 1 mole on top. Okay, and this is of course 1 mole of O2. However, my problem's not asking me for 1 mole of O2. So I got to go that step further. So I'm going to add onto my thing, onto my fraction table, the next step, and I'm going to then put in my molar ratio, which we solved in the last step. And so our molar ratio is that there's 2 waters, and remember I want to use what I want, my moles that I want on top, and my moles that are given to me, my O2 on the bottom. So it's 2 to 1. Okay, so I have my 1 O2, and again, the reason I know is I can always cross out matching words. Okay, and then 2 H2O. And so once I cross out everything that matches, so I cross out grams and grams, moles of O2 and moles of O2, I'm going to multiply across and divide by the bottom, and I get 0.31 moles of H2O. So that's how I'm going to convert from grams of one compound to moles of another. That molar ratio is very, very important. Okay? Now, we don't measure in moles. Like you can't put moles on a scale. So we are going to have to go a little bit further sometimes if we're trying to figure this out. And that's what the next set of slides is going to show you. So let's go take it one step further and determine the amount of a product made or the amount of reactant needed to complete this reaction. Okay? And you can do this with anything. So if it's asking you grams of compound A to molecules of compound B, you can use the conversion factor of Avogadro's number. Later on, when we get to another unit, we're going to show you another conversion factor that you can use in these types of equations. So it's just really important that you know that you don't always have to go from gram to gram. You can go from molecule to molecule. You can go from molecule to gram. You can go to this new conversion factor, which we're going to teach you in Unit 6. All this stuff can happen, but it's the same process. Just make sure you're using the right conversion factor. So, same problem, except for this time, instead of asking me how many moles of H2O, I changed it to how many grams. So this is going to look very similar to what we just did. We're just going to take it a step further. So again, I need to figure out my molar mass of O2, which again is at 32. 16 for the mass of 1 oxygen times 2 because there's 2 atoms of oxygen in my molecule. I'm going to draw my fraction chart. I'm going to write my given, which is 5 grams of O2. I'm going to put my molar mass on the bottom because I want to make sure I cross out grams, and I'm going to do it's grams per mole. I'm going to add another section, okay? So just like we did in the last step, okay? And now is the perfect time to switch compounds, okay? And again, I'm trying to find H2O, so I'm going to use that molar ratio of 2 H2Os to 1 O2, and I got that again from my balanced equation. Okay, so 1 mole O2 to 2 moles of H2O. Okay. Now, this is where we stopped last time. Now we're going to take a step further. I'm going to go to grams. Because I need to go to grams, I need to look at the molar mass that gram is associated with. So this time grams, the bridge of attaches to H2O. So I need to figure that one out. And we have figured out the molar mass of water in the past. Okay, so again, I'm going to add my chart piece. Water has a molar mass of 18.0 grams per mole. And if you forget how to do that, water, H has 1, and there's 2 of them times 2. Oxygen has 16. 16 plus 2 is 18. To get rid of mole of H2O, I got to put mole on the bottom. Okay. And then, of course, I want to put the units that I want on top, which is grams. And I'm going to put the numbers that match these words. Okay. So I'm going to drop my numbers in. I'm going to cross out everything that matches. So gram and gram, mole and mole, mole and mole. That leaves me with grams of H2O. I'm going to multiply across and divide by the bottom, and I get 5.6 grams of water. So if I use 5 grams of oxygen, I'll make 5.6 grams of water. Okay, so that is how you do stoichiometry. It's very simple. It's very easy if you take it one step at a time.